Hey, welcome to 1.2. We're looking at the Ready, Set, Go. I'm Mr. Cortez. Hope you're doing well. As a refresher, this is Integrated 3. Still glad you're here. Thanks for sticking with me. We'll be talking through some of the problems in the Ready first. So here, we're just solving for x. Some of these are pretty simple. This should take 2 steps. Problem 1. Problem 2 we'll look at. That looks like a good time. So we have x squared on both sides. We have x on both sides, which is okay. If we deduct 2x squared from here, deduct 2x squared from here, that can get us in the right direction. We could also bring 5 over and see where that takes us, because now everything that's on the left side is canceled. We're now left with 0 on the left side. This equals x squared. We're deducting 12x, and this is going to add on 5 to 31 to get 36. So does this look like something we could factor? What do you think? Hopefully you're saying this can factor to x minus 2 being squared. And if you continue to solve this, take a square root, take a square root. Square root of 0 is 0. You're left with x minus 6. Normally you would think plus minus 0 here, but it's not quite like that. Then you can just add on 6. And x is 6. Boom. Good. There you go. We'll look at 4 since we're here. We have everything under the square root, so let's break it out of jail. Let's do a prison run. Let's square everything. Let's do x squared plus x minus 2, because that's what's left over. And 2 squared equals 4 on this side. This looks as if it's going to be approaching a factoring situation, so we'll entertain it. X squared's left plus x minus 6. This all equals 0 now. Does this look like something we could factor? X squared plus x minus 6. Can you think factors of -6 that add up to 1? Hopefully you're saying 3 and -2. So we can jump back and say, this is really x plus 3, x minus 2 equals 0. You can set both of these equal to 0 and solve, but you're just going to get kicked back that x equals -3 or 2. Peach, does that make sense? You can plug them back in if you would like, but those answers are going to be pretty legit. We have the elephant in the room here, this cubic root of 5x plus 1. Let's break it out of jail. Let's cube it. We saw this in 1.1. There was a problem that said if there's a cubed root, you can undo that by cubing both sides. So taking it to the third power, this is now not -16, because that's just when it's squared. It's going to be -64. And this should equal 5x plus 1. Two-step equation from here, get rid of the 1. -65 equals 5x. Solve that. You now have that x equals -13. And so the fact that this is a cubic root doesn't quite matter, because if you plug back in, you can take the cubic root of a negative number. And we'll even test run it here if you're so inclined. If we have the cubic root of 5 times -13, that's going to be -65. And if you add on 1, you're pretty much being asked what times itself 3 times gets you -64. And that's definitely going to be 4, -4 in particular. So we're good here. For this problem, they're both under cubic roots, so set them equal to each other. You're pretty much just solving 352 equals 7x squared plus 9, which might seem a little tough, but just try to isolate x. So try to isolate x, get rid of this 9 from here and here. And then you're still left with 7x squared, and you got it from there. And sorry for the cliffhanger on this, but we'll take this a step further. This leaves you with 343 equals 7x squared. You can divide by 7 here and here. So you're pretty much solving 49 equals x squared. So x, in this case, you get two answers. That's okay. It can be plus minus 7. Plug it back in. If you're not convinced, check it. There you go. 8's a little cryptic. It's pretty much saying there's some exponent for 5 that would equal 1 over 125. So this you might need to get a little big with the arithmetic, kind of throw some things together. So I know that if I did 5 times 5, that's 25. And then if I did 25 times 5, what does that get you? Boom, 125. So really, I could pop back here and say that this is 1 over 5 to the third. Because if I do 5 times 5 times 5, that equals the head honcho 125. That being said, you might not like how this is in a fraction. So recall that if you have a term in your denominator, you can pop it back out and make it a negative exponent. And that is totally fair game. So here, notice how our bases are both 5. Our exponents pretty much saying x equals -3. So that's that. The previous problem is similar. So is this one. You'll have to think out maybe more so factors of 2 for this. So think out with this one. Although this is 4 to the x, you can really treat this as 2 to the 2x power. And then maybe think out 1 over 32. Can you rewrite that as a base of 2? And then can you take that further? So that's the ready. We'll look at the set next. So welcome to the set. Problem 10. You have these two jabronis, Ethan and Emma. They saw each other's graphs and exclaimed together, your graph's wrong. And they're saying, the integrated lords, that neither graph is wrong. So we're explaining what Ethan and Emma have done with their data. So I know from Ethan's graph, we have this point 1, 1, this point 4, 2. There are other points, but those deal with fractions, and who's got time for that right now? So we know those points are there, but what do we notice about Emma's graph? Set up a little table, keep it organized. Still, that point 1, 1 is there. What other points now talked about? What other points now in the mix? 2, 4 is there. So a few things you can say. Since these points swapped places, like how, I mean, the 1, 1's not the best example, but hopefully you can agree that from Ethan's graph to Emma's graph, your x and your y's switched. So some things you could say that the domain and the range switched. You could also say that these are inverses of each other. And I guess if you want to really simplify it, you could say that the inputs and the outputs switched. I'd say that's a pretty good summary. Describe a sequence of transformations that would take Ethan's graph onto Emma's graph. We haven't seen this done too much in 1, 1, and maybe in 1, 2, we'll see it a little bit more. But a common feature of inverse functions is that if you reflect them over this line that I just drew, y equals x, and maybe this might be something that you test run, double check that this works. If you reflected all of these points over the y equals x line and vice versa, they would map out onto each other. So what could you do? You could mirror or reflect over y equals x. That's fair game. You can sketch it out. You can try it, but that's something you could do to show that Ethan's graph could eventually transform over to all of the points that Emma has graphed. Where are my ballers at? My base ballers, my physics peeps. This is going to deal with a lot of something you'll see in physics. We're using this graph to answer the questions that are below, but the questions below are something like this. They're asking, what's the highest point of this baseball when it's hit upwards? It is ballpark to be like 100-ish feet. But where does that occur after how many seconds? It's about to be 2.5. So I'll do my best to kind of write my answers here. So after 2.5 seconds, it's at the highest point. I think part B asks, how many seconds does it take for it to return back down to Earth? You could say that it's like 5-ish seconds. That's fair game. Part C asks, how at 67 feet in the air, what time does that happen? We see that 67 feet's about here. So notice these points are on the same level. This occurs at 1 second and also at 4 seconds. So at 1 and 4 seconds, the height is approximately 67 feet. So we have two answers here at 1 and also 4 seconds. So that's part C. So part D has you graphing now when height is an input, what's the time in seconds? Some points you could throw in here are as follows. We said that if it's at height 0, chances are no seconds have passed. That being said, there's also this point that we talked about back here where if the height's 0, if it takes the trajectory around 5-ish seconds, it's back down to the ground. Okay. So some other points you can map out, which we already talked about. We said that if the height's 67 seconds or 67 feet, recall this is in feet, not the things you walk on, but the distance measurement. 67 feet, that happens at 1 second. But where else? It also happens at 4 seconds. And we also said that around 100-ish, that's going to take 2.5 seconds. So as far as clarity on the graph, make it look like a parabola, honestly. It should look similar to the previous graph you did. Make sure it has that curve. Do your best to hit these points. Aim for the stars. So your graph could look something like that. That's totally fair game. Of course, use your best judgment with the points that are here or make the points a little bit more noticeable. But that's an approach you could take for graphing this. E is asking, new graph is the inverse of the time versus height graph. That's no doubt, but it's not a function. And why is that? Well, if you do this vertical line test, this is a little conflicting, the fact that it hits two values. And this right here is a giveaway that this is odd because you have the same input with different outputs. Think about that. You might have saw an integrated 1 or 2. You had, table like this, and you had values that it would shoot to. This right here was a giveaway that it wasn't a function, so it's no good. That being said, how would you restrict the domain on the original function to make it invertible? Well, we know that the first half would be fair game, and it's after this vertex, even though it's on its side. After the vertex is where it kind of goes to trash, where now we have these other values repeated. So you could restrict this from here to here, from the 0 to the 2.5. That would be legit, because that would not only cut the parabola in half, so that you're only dealing with this, but it would also get rid of this second half, which is kind of the area that's throwing us off. So that's why down here I'm saying we would just restrict it from 0 to 2.5 for the domain. And again, domain's talking about your input. Peach, makes sense. The Go has more values. that are given, f, g, h of x. I think most of these we've done before, so plug and chug. You might see this notation down here, so this might be something we talk about. The composition of f of g of x and f of h of x and g of f of x. So notice the function notation f of g of x is indicating that you replace x in f of x with g of x. So we need to do a little bit of work. So let's recall what we're working with. We have g of x equals 10x plus 4. I'm going to just rewrite these. I'll pause the video in a second and we'll meet back up. All right, so I rewritten the functions. I suggest that you do the same so you're not flipping back and forth. What's this bit here saying? On the outskirts, you have f, but inside you have g of x, and we know g of x is 10x plus 4. And so this doesn't mean that we're done. We really just took what g of x was and just substituted in something else. So now we have to take this a step further because we're evaluating f, where the input is 10x plus 4. So what does that look like? Recall that f of x is 3x. So instead of x, we're now putting in 10x plus 4. And this is something we can take further. We distribute it up. That gets 30x plus 12. So this would be considered f of g of x. 30x plus 12. Notice how our answer is not just a normal number because these functions have more to it. Maybe take a moment, try f of h of x, and I'll throw in some answers for that shortly. So you could start by saying that on the outskirts, we're dealing with f, and our input is h of x. Recall h of x is x squared minus x. So now we're dealing with f of x squared minus x. So similar scenario, wherever x is though, we're now putting in x squared minus x. So then we can distribute that up. 3x squared appears, and we're deducting 3x. Capiche? We're done. So this was our answer over here. And I guess take a moment, why not? While we're here, try g of f of x. So think, you have g on the outskirts. What's f of x going to be in there? Hopefully you're recalling that f of x is 3x. So now we're evaluating g of 3x. So let's run back. We know that g of x is 10 times your input plus 4. Our input here is 3x. Distribute this up or multiply it. So in this case, 30x plus 4 is our answer for this. And we're done. There's nothing you really need to solve for. You just need to know what is your input and that you have to take it to the rest of a function. So I hope that this video was helpful. Sorry for the bell at the beginning of this. If you have any questions, reach out. Thanks for watching.